My name is Tinashe Rowana, and I'm a toxicologist here at the Institute for In Vitro Sciences, in charge mainly of the skin sensitization program. And a little bit about my background. I have a PhD in chemistry, and my bachelor's degree was in biochemistry. And I always tell people I've done a lot of research in so many different areas, but then after having done my undergraduate in biochemistry and also doing a lot of chemistry for my PhD, for my postdoc, I took a completely different route altogether and went more into virology and vaccine development, where I was using a lot of animal models. And subsequently, I got a position as a research scientist where we were doing influenza research on different animals. But one thing that I observed in all these things that I was doing for my career was that a lot of times some of the animal models that we tend to use don't necessarily agree with the human data or are not necessarily toxicologically important in terms of some of the disease mechanism or some of the endpoints that we would be testing. And I became more interested in alternative toxicology, and that's what led me to the Institute for In Vitro Sciences, where I'm in charge of the skin sensitization. And on top of my PhD in chemistry, I'm also board certified by the American Board of Toxicology as a toxicologist, mainly in general toxicology. So today I'm going to talk to you a little bit more about integrated testing strategies for assessing skin sensitization potential for chemicals. Here's a brief overview of the talk. I'll start by talking a little bit about some of the biology for skin sensitization and then move on in some of the current testing strategies are being currently used, including the in vivo and then also alternative methods, a little bit about in silico and computational, but I'll talk more about some of the cell-based and then chemical assays which are being currently used, particularly in the EU and also here in the US to look at skin sensitization. And in particular, the specific assays that I'll spend a little bit time talking about include the direct peptide reactivity assay, keratinosense, and the human cell line activation test. And then I'll briefly talk about some of the strategies that you can be able to use to do your hazard determination using these methods, because these methods on their own, you can use them for initial characterization, mainly for hazard identification. But in terms of overall safety assessment, you have to use them in an integrated testing strategy. And then I'll end with a few special considerations to look at some of the chemical space, which is not necessarily fully represented by these methods. And I guess we can all appreciate the fact that even the animal model or any model might not necessarily be that useful depending on some of the specific chemistries that you'll be working with. And there's always need for you to understand some of the limitations of the assays that you would be using. So here, I'll give a brief biology of skin sensitization. So skin sensitization is an immunologically determined adverse reaction which happens in two phases. The first phase, called the sensitization phase, is after you get exposed to small, low molecular weight molecules which have to penetrate into the skin. And these low molecular weight compounds usually have a molecular weight of less than 800 kilodaltons, and by themselves are not immunogenic. Therefore, the immune system cannot be able to recognize them. But then after they bind to some of the endogenous host proteins through a process called haptenation, and then they are now recognized by dendritic cells, which will now uptake them and process them now. And after that particular processing, they are now presented to naive T cells here, leading to clonal expansion and also memory formation. So and this happens mainly in the lymph nodes. And once you get upon re-exposure with the cell molecule or other molecule of structurally similarity, it will now cause the recruitment of T cells and other immunological cells to that point, leading to inflammation. So this is the allergic contact dermatitis that you will now get upon re-exposure to the same molecule, leading to the adverse outcomes. And this is not something that you would want any product or any chemical to have. And in terms of some of the common cases where you get allergic contact dermatitis, include people having tattoos and reacting now to those particular tattoos, and also the use of gloves. They used to use some accelerants in making gloves, which would lead people to have this allergic contact dermatitis. And ordinarily, some of the common sources of some of these common allergens that people will get exposed to either occupationally or in our everyday living include epoxy resin systems, remain like adhesives and paints. You have formaldehyde, which is used as a pesticide and also in common household cleaners, and then fragrance mix for toiletries and cosmetics. You have neomysulfates for mainly also for cosmetics, and some of the common metals include the nickel sulfate, which is a common material used for jewelry, tools, etc., etc. So inadvertently, within our everyday living and also occupationally, like I said prior, we get exposed to some of these potential allergens, which can lead to skin sensitization. Therefore, it is very important during product development or otherwise to assess the potential to cause skin sensitization. So in terms of the animal-based testing, here are a few methods that have been developed, and also some of them in current use include the guinea pig maximization test, mouse ear swelling test, and the local and lymph node assay, which is the gold standard for using animals to test for the skin sensitization potential, but also have human patch testing, where a small amount of chemical is put onto the surface of the skin, and then you look at the responses after 24 to 72 hours. So there are a couple of ethical concerns for using humans for your testing, and usually it's only used more towards the end of the product development when you've done most of the initial characterization either in vitro or in animals, and then you can be able to do first in human trials to see the performance of those particular compounds with humans, in particular if that product is going to have some skin contact of some sort within its usage or otherwise. But some of the more alternative non-animal based testing include in silico assays. So because we now understand a lot of the chemistry of chemicals which have the potential to cause skin sensitization, so by looking at the chemical structure, doing read across and other strategies, you can be able to predict whether a molecule will cause skin sensitization or not. So therefore, you can be able to use some in silico computational tools, but then also other tools that you can be able to use include in chemical reactivity assays, and there's also a lot of in vitro or cell-based assays, and I'll show you in the subsequent slides that indeed within the space for relevant assays, a lot of assays are covering the in vitro and cell-based arena. So for the animal tests, which has been used for a long time, include like the guinea pig or the Buller assay, where you topically apply your antigen or the test compound that you're working with or without an adjuvant, and then which is like the induction phase. Then after a couple of weeks, typically 20 to 28 days, you now challenge the animal with that chemical, and then you look at the induction of allergic contact dermatitis. So as a model, this model actually looks at allergic contact dermatitis as the end point, because you look at the immune response that you have upon re-exposure to that particular chemical. But some of the limitations include the fact that this is a very subjective test in which the technician or whoever running that assay has to physically look at the induration or to look at to see the level of the inflammation. and then do a scoring that you can be able to relate to the concentration for your potency determination. But in any case, it gives you the model which looks at the entire allergic contact dermatitis. Another method which was seen more as a refinement from the guinea pig maximization test is the local lymph node assay, which uses mice, in which you have your mouse and then you administer the test material or article that you'll be having over 3 days with a vehicle, usually acetone or olive oil, and then afterwards you now challenge it with you add some thymidine, and then you look at the proliferation of the local lymph node assays now, and then using scintillation counting. So this is a radioactive based method, and then you can be able to come up with a stimulation index of something being a sensitizer. If you have an SI greater or equal to 3 and it's less than 3, then it will be a non-sensitizer. And subsequently, they've also tried to improve this method by using ELISA determination as opposed to using liquid scintillation counter. So in that particular instance, that's the BEDU ELISA, which is a dye, and you also look at the lymph nodes to see the proliferation after your cell suspension, and you use a stimulation index of equal or greater than 1.6 for a sensitizer and less than 1.6 as a non-sensitizer. And also by using different dosage groups, you can be able to do some potency determination other than necessarily just hazard identification. And since we now understand a lot of the biology and the chemistry which leads to skin sensitization, the OECD in 2012 came with an adverse outcome pathway which can be used to represent the entire pathway from the molecular initiating event to the organismal responses. And within this particular adverse outcome pathway, which includes things I said talked about before. So some of the in vitro or non-animal assays that you can be able to do include the in silico toxicokinetics, QSA, and then also when you look at the chemical structure, metabolism, or electrophilicity, these are things that you can be able to look at and characterize prior to doing any studies, and this will be able to give you information on the potential of your molecule to cause any skin sensitization. But the molecular initiating event, which is key event 1 here, is the most important aspect for skin sensitization. So therefore, this already precludes things like metals or other substances which use alternative pathways to cause allergic skin dermatitis. But most molecules which are electrophilic, which would bind to nucleophilic centers within your cells, that this covalent interaction is the first key event. And for that, there are a number of assays which can include peptide depletion, adduct formation, or some of the relative reactivity rates that you can be able to characterize the initial covalent interaction, which is the first key event. And that is followed by key events 2 and 3 within keratinocytes and also dendritic cells. And for that, we have various biochemical pathway activation, gene protein expression, various pro-inflammatory cytokines, and then also the expression of co-stimulatory and adhesion molecules. And these are more of the cellular responses that you'll be getting. And then on the organismal response now, we have the in vitro T-cell priming or proliferation. And currently, a lot of methods are available for key event 1, 2, and 3. And for key event 4, we don't have any in vitro assays available. And to look at some of the specific assays now within the adverse outcome pathway. So like I said earlier on, for molecular properties, you have various in silico and also structural activity relationships that you can be able to look at. And then for the molecular initiating events, we have an OECD guideline 442C for the direct peptide reactivity assay. We also have the peroxidase peptide reactivity assay, and this mainly tries to account for metabolic activation of some of these particular chemicals. And then for stellar responses, where I said we have a lot of assays available, and some of the main ones which already have OECD guidelines include test guideline 442D, which is the keratinosense assay, and also the HCLAT assay test guideline 442E. Though there are several which are still under development, including the Lucens assay, the Sensitization assay, USense, GUARD, and various other cell-based assays that people are developing, which can be able to be used to predict skin sensitization. And for the purposes of this particular talk, I'll talk more about the DPRA, keratinosense, HCLAT, a little bit of Sensitization, and also the GUARD assay, just to give you a flavor of the methods which are currently available. And then for the organism of response, we have the local lymph node assay, which also has an OECD test guideline 429 and 442A and B, and also the human proliferation assay, though these assays currently don't have any test guidelines. And then the human patch repeated test and the Buller assay are now the organismal responses. So I'll talk a little bit more about the molecular initiating events, DPRA assay, the cellular responses, keratinosense, and the HCLAT assay. So the direct peptide reactivity assay. So this is an assay which addresses the molecular initiating event, which is the key event 1. And for that, you look at cysteine or a lysine peptide percent depletion. So here the model peptides that you use in the assay, and this has the cysteine and the lysine residue. And both of them have phenylalanine here, which is the one that you use for HPLC detection. Because after you do your elution, because you look at the UV detection at 220 nanometers using the phenylalanine residues here. And to do the assay itself briefly, for the cysteine residue, you do a 1 to 10 mix, where 10, the excess will be your peptide, and for the lysine, you do a 1 to 50 for 24 hours. And after 24 hours, you now look at the free peptide that will be available. And here, if you look on this upper corner, let's say this is your chromatogram, this would be your unreacted peptide. And then after you react with your test chemical, you can look now at the reduction of this particular peak of your unreacted peptide, and then use that level to do your model prediction. In this particular case, purely for hazard identification, if you have a mean peptide depletion, either of the lysine or the cysteine or combined, of 6.38%, that's the threshold that you use to determine whether it's a sensitizer or a non-sensitizer. In terms of the applicability and limitations, this is purely a chemical system, therefore there's no metabolic activation. Therefore, prohaptens, which are chemicals which need prior activation, for example, benzoylpyrene, for them to become reactive, you cannot be able to detect them using this particular method. And then also it's not applicable to metals, oxidizers, or highly hydrophobic chemicals, or any of the mechanisms which don't go through covalent interaction between the nucleophile and the electrophiles. Then the second method is the keratinosense assay, which is an OECD guideline 442D, and this mainly addresses the keratinocyte responses, which are caused by the activation of some danger signals within the antioxidant electrophile response dependent pathway. And mechanistically, when you have the hapten binding on to sulfur hydro groups within the KEAP1, cause the dissociation of the NEF2, which will now migrate into the nucleus, where it binds to the antioxidant response element. In this particular instance, you have a luciferase gene downstream of the ARE. So if it is a sensitizer and it binds to your KEAP1 and then NEF2 goes inside the nucleus, would now cause this dissociation and then also the subsequent upregulation of your luciferase gene. And then you look at the light emission if you add in a luciferase substrate. And And for this particular assay, you use the HCAT reporter cell lines, which you incubate with your test chemicals for 48 hours. After 48 hours, you now add your substrate and do a luminescence reading. And in terms of the prediction model, you look at the gene induction and also cytotoxicity. And as you can see here, if you have a non-sensitizer, so here on this axis, we have our fold induction for the luciferase gene, and here is your viability. And if you have a non-sensitizer, then you have your cytotoxicity above 70%, and also your gene induction below the 1.5. But if you have a sensitizer, you have your gene induction going above 1.5 with your cytotoxicity still very high, above 70%, and you now use this for your determination. In terms of some of the limitations, so since it's a cell-based assay, it means that your test article has to have low cytotoxicity and also has to be soluble with solvents which are compatible with the system. Therefore, it has to be DMSO or water-soluble compounds. And also, I said that the hapten has to bind with the sulfur hydro groups on keep one. Therefore, it is biased towards the molecules or chemicals which react with the nucleophilic cysteine sulfur hydro groups. And the cell line too has some limited detection for prohaptens since the metabolic capacity is limited. And for the human cell line activation test, which also has an OECD test guideline 442E, it mainly looks at the dendritic cell responses by measuring the co-stimulatory and adhesion molecules. And this assay addresses the third key event. So you look at the cell surface markers CD86 and CD54 by flow cytometry. So it has some dose dependence because you use like 8 doses. And after 24 hours, you look at the relative fluorescence intensity for CD86, which has to be greater than 150%, or for CD54, it has to be greater than 200, and you use that now for your prediction model. In terms of some of the limitations, some of them are common with the keratinofens since they are both cell-based assays, and also inherently for this particular assay has a very high false negative predictivity, particularly for chemicals which have a high log KO. Therefore, the solubility in water, if it is not highly soluble in water, this assay gives you false negatives. And then other assay, which I'll talk a little bit about, is the GARD assay, which has an OECD test guideline pending, but it's the genomic allergen rapid detection, where you use the MAS3 cell line with your test chemical, and then the assay is based on differentially regulated transcriptional changes of selected genomic markers, which are referred to as the GARD prediction signature, and they probe here more than 200 genes, and they have a support vector machine model trained on 38 reference chemicals that you now use to do your classification on whether something is a sensitizer or a non-sensitizer. And as you can see, since we look at more than 200 genes, it's a more complicated assay, but gives you more information. And the last assay that I'll talk to you is the Sensitization assay. So the other two assays which I've talked prior, they're cell-based assays which you do more or less on a 2D, like on plate-based, but this one uses a human 3D reconstructed human epidermis, and in this case the episkin model, and the analysis is by reverse transcriptase PCR, and you can be able to use different concentrations to get some idea about the potency of the chemical that you'll be having. So you apply the chemical onto the skin model, and then after a couple of hours, you do tissue lysis, RNA extraction, and the reverse transcriptase PCR quantification. And in terms of the prediction model, you can look at irritation. There are 24 genes specific for irritation. So if you have at least 7 of them upregulated or significantly induced, you can use that for irritation. And then for sensitization, you have 7 out of 24 genes within the antioxidant response element group, or 7 out of 21 genes within another class of gene called the sensor S gene signature. So if any of those ones are significantly induced, then it is a sensitizer. And since you use 4 different concentrations of your test material, and depending on the concentration that you get that significant induction, you can be able to use that for potency assessment. And the last thing here on this particular slide, IIVS has been involved in the development of some of these particular assays. For example, for the keratinosense, we did the inter-laboratory studies in 2009, 2010, which were used for the ECVAM validation exercise, and we've been offering it commercially for a number of years now. Also for direct peptide reactivity, we have done some extensive training with Procter & Gamble, who developed the assay, and also for HCLAT, for Shiseido and Kao, we've worked hand in hand with them in terms of running this particular assay. So we have a good wealth and understanding of running these particular assays, and currently we are also doing further research to see how we can be able to combine these assays both for single components and also for complex mixtures to improve their power for the prediction for skin sensitization. So in terms of how can you be able to use all these assays within your strategy, currently the guidelines are very clear that you can be able to use these methods for discrimination of sensitizers and non-sensitizers in combination with other complementary information. And since there are limitations to each assay, an integrated approach is better than a single approach assay. And if you are going to do more safety determination, then all 3 assays should be used. And since they're only used mainly for hazard identification, you cannot be able to use them for any potency categorization. Therefore, putting chemicals in the UNGHS subcategories 1A or 1B cannot be done using these assays. And for individual chemistries or approaches that organizations can be able to use, the best strategy that you can be able to do is the one that is quite unique to you. So depending on the chemistries, or whether it's standalone for internal work, or just screening before you do any animal cleaning testing, or whether it's for submission or the running cost, the timing or the cost involved, whether you can do it sequential or in parallel, but also the risk of the products that you'll be developing. So all those are some of the important considerations that you need to make. You have to come up with a good integrated testing strategy. So yes, just an example where we can be able to use all those in vitro assays I talked about, keratinosense, peptide reactivity assay, HCLAT assay, or any other in vitro data, and do them for hazard categorization so you get a plus or a negative. And then you can be able to put all that information into your weight of evidence now for your hazard classification, for the potency determination, now using your computational human data, some in vivo data if you have it, and then also any other additional data that you may be having. And hopefully with time, these in vitro assays will gain enough confidence that we can be able to use them on their own to do the hazard classification without using any of the other additional assays, in particular the animal assays. And here's an example of one of the common strategies that people are using for hazard identification. So if you can use key event 1 or key event 2, and if any of these 2 methods agree with you, then you can classify based on those particular 2 assays. And if they don't agree, then you use a 3rd method now with the other key event. So if that's key event 1, key event 2, this would be like a key event 3. And if you had used the key event 1 and key event 3 here, this would be like key event 2 assay. And then based now on the 2 concordant results, you can do your classification. And as you can see here, it has very good sensitivity, specificity, and accuracy for these chemicals that they used in this particular testing strategy. And these are all the simplest strategies that you can be able to employ. Though there are some other ones which are more complex. For example, here, the Bayesian Network, which Procter & Gamble mainly uses for potency prediction. As you can see, the probabilistic model, which uses animal data, and then you have your computational, and then you look at the solubility, you look at the deeper assays for the lysine and the cysteine, and the cysteine and the lysine. You look at CD86, the H-class assay, and then you also have, the IC50 and the various other things, like carnosine assay, and you use a multiple number of endpoints into this particular model to do your potency determination. And currently, the OECD level, they have about 12 methods which have been submitted to them to look at some of these particular integrated strategies, and various organizations and companies use different ones, but hopefully with time, we'll be able to come up with more defined approaches which individuals can be able to use in their safety assessments. Lastly, within the testing strategy, I think a very important thing has to do with what type of assays you do within the adverse outcome. So depending on the strength of evidence based on reliability, relevance, and concordance, if you are doing initial screening within an organization or a company, you can only use the molecular initiating event just to do the initial screening, and as you start to prioritize, you can add one key event, and as you do more and more things now to hazard assessment, you now start to use the entire adverse outcome pathway. Therefore, your strength of evidence now has to be very high to involve the different aspects within the adverse outcome pathway itself. But sensitization is one area in which the advances in science has enabled us to be able to come up with the adverse outcome pathway where we can be able to do some of the assays upstream of the actual adverse outcome, allergic conduct dermatitis, and be able to predict the potential for causing the adverse outcome by using various key events which will be further upstream of that entire adverse outcome pathway. So lastly, some of the special considerations is that since we can't have a one-size-fits-all, sometimes you have testing of chemicals which are mixtures, and since these methods are mainly developed and validated using single component chemicals, so there is need for us to be able to do more testing and see their predictive power when using mixtures, since ultimately people get exposed to complex mixtures of botanicals or other substances of undefined chemicals, constituents. So there's need to see if these methods can be adapted, or newer methods can be adapted to be used with these mixtures. And then also the other chemicals like prohaptens, which need some metabolic activation. And so since cell-based assays have limited metabolism and the DIPRA provides no metabolism, and people have been looking at the hydrogen peroxide system, and also the use of human liver microsomes as useful additions to chemicals which require some sort of enzymatic activation. And then also probably Alison talked about this, but it's also need to understand chemicals which need photoactivation prior to them being sensitizers, and to see can we be able either to modify existing protocols or to develop new protocols which can be used to look for chemicals which cause photoactivation. And thank you for listening.